Yes, good morning.
Yes. Thanks a lot for the introduction. So I'm glad to be here today and speak about how we can model and individualize learning in computer-based environments. So I will talk about classic personalization in online learning systems. So as we all know, human teachers, or when it's one-to-one at least, they are professionals at exactly providing this adaptation. So they personalize their interactions and also their instructions, and they don't take into account only the knowledge of the users, but they also check what strategies the student might use, the preferences the student might have, or they also analyze their misconceptions. So of course, our goal should be that we want to match this human quality adaptation with our systems. So how does this adaptation work in the computer? So first we have the students that interact with our system and we collect all kinds of data. Like they write, they click with the mouse, there might be speech data, video data, and so on. And the key challenge is now that we make sense of this data and that we build models that are able to, for example, represent and predict the knowledge of the user, their learning, their strategies, their engagement, whatever we want to adapt to in our system. And based on the predictions of these models, in a next step, we can then provide an individualization. And again, that can have different forms. So we might be interested in selecting a task, giving a feedback, or providing a targeted hint. And what I will speak about today is just this middle part, how we can represent and predict the knowledge and the behavior of the user in the system. In the first part, I will cover the traditional approaches that take into account the knowledge of the user, so right, wrong answers to specific questions. And in the second part, I will give some idea of how we could also assess and model the strategies that users use in a more open environment. So if we want to adapt to the knowledge of the user in a system, we first need to have a representation of that knowledge, and then we need to update this representation based on the interaction of the user with the system. This can, for example, be the solved tasks. So let us just assume in a simple case, we have a student who is trying to solve subtraction tasks between 0 and 10. So here the rectangles denote the task, the zeros are wrong answers, the one correct answers. We have observed this sequence of n tasks, and now the question is, what is the probability that the student solves task n plus 1 correctly? There is a very popular approach of exactly doing these predictions. So we introduce here a second variable, the blue circle, and this basically denotes whether the student already knows this skill, subtraction between 0 and 10 or not. And as we cannot see into the heads of our students, we assume that this variable is hidden. However, we can infer it by observing answers of students to tasks, so these square rectangles that are associated with the skill. This approach is called Bayesian knowledge tracing, and it needs only very few parameters. And these parameters are associated with learning. So here, the transition probabilities are associated with learning a previously known skill or forgetting something that you have already known. And then here, the emission probabilities, they are associated with guessing the answer to a skill that I don't know yet, or with making a mistake when applying a known skill. So the nice thing about this model, or why it is so popular, is that it is interpretable, the structure is easy, so parameter learning and prediction are very efficient. However, if we want to model several skills or knowledge components at the same time, for example here 3, we need to train 3 different models. Many learning domains, such as for example mathematics, are however hierarchic, so the skills are related to each other, and using this type of model we cannot represent the relationships between these skills. Dynamic Bayesian networks, on the other hand, are able to represent hierarchical relationships over time. Therefore, we saw the opportunity to adapt these dynamic Bayesian networks for knowledge modeling. So here you can see 3 skills, and here we would assume that the orange skill can only be learned if the blue and the green skill have been learned before. So as a concrete example, we have designed a dynamic Bayesian network for elementary mathematics learning. And this is just an excerpt of the network. This is addition and subtraction between 0 and 100. And here we, for example, assume that addition with the carry is harder than addition without the carry. And the full network has more than 100 skills and has been designed together with domain experts. And it is currently implemented in a software for elementary school children in Switzerland and is also used by 30,000 elementary school children. Of course, when we have now this structure, this is way more complicated than the Bayesian knowledge tracing approach, and therefore we also had to develop an algorithm which is able to efficiently learn the parameters in this network. So, but the question now is, how does this perform compared to Bayesian knowledge tracing? And here I just talk about predictive performance. So we took the two approaches and compared them on 3 different data sets. So the prediction error here is the root mean squared error. The subtraction data set is our own data set from our own software. The algebra data set comes from the cognitive tutor that you have seen before. And the physics data set comes from another tutor in the US, the Andes physics tutor. And as you can see, the dynamic Bayesian network outperforms this Bayesian knowledge tracing approach, and although the differences are small, they are all significant. So that has been a short overview of more traditional models of knowledge, and more recently, people have also experimented with using neural networks to predict the knowledge of the users. So here we have a recurrent neural network, and it's called deep knowledge tracing. So it's based on the idea of Bayesian knowledge tracing that we have seen before. Again, the blue variables here, they denote the hidden state, the hidden layer of the network, which is supposed to capture the relevant information about the knowledge of the student. Then here, the green one are again the observations. So here we have 3 skills, 0, 1, and 2, and it's a one-hot encoding, so we have them twice, once for correct answers and once for wrong answers. And then, similar to the Bayesian knowledge tracing model, we have an output layer where we predict the probability that the student has learned a skill or not, or will solve a task associated with a certain skill correctly. So now the question is, how does this perform? Unfortunately, I have a comparison with another predictive error measure because the authors of this newer approach have used the area under the receiver operation curve, and you can see that on different math data sets from the US, the deep knowledge tracing outperforms this Bayesian knowledge tracing approach by a lot. So what can we say to summarize? So of course, Bayesian knowledge tracing is simple, efficient, and interpretable, and that's why it is widely used. Dynamic Bayesian network then can represent also the hierarchical relations between the skills, which improves predictions, but the model is also more complex. And then deep knowledge tracing can also learn linear relationships and implicitly captures the relations between the skills, but is of course again more expensive to train. So that was a short overview of how we can model the knowledge, so the right, wrong answers of the students. And in the second part, I would just like to give you a short idea of how we can also look at students' learning strategies. And I'm doing this by using data that was collected from an environment where students learn Newtonian physics through a simple tug-of-war game. Let me just start. Yes. So here in this game, students can choose how they learn. So they can have the simulation mode. They set up teams and they can see who will win the game. And then there's a second mode where they are asked questions and they have to say who will win the game. And this game was originally designed as an assessment. So the idea is that students learn the mathematical relationships that govern these tug-of-war games, but students, when they start the game, are not told that this is actually the goal of the game. So how it works is they just get an intro on how the game works, and then they can go to what we call this challenge mode, where they have to determine the winner of given configurations. If they do a mistake, they are kicked back into what we call the simulation mode, but they don't have to stay. They can just go back here and answer further questions. If they get a question correct, they get a new question. And after 8 questions of increasing difficulty in a row, we give them a post-test to check what they have learned from the game. And as you can imagine, in this game, it doesn't make a lot of sense to just model the right, wrong answers of students in this challenge mode and try to predict them, because what matters is also what they test here and how they change in between these 2 modes. So what we have done here then first is a cluster analysis where we have looked at their trajectory through the game. And we have done this on different data sets. I will just give you an example. This is a school in California. And we found 6 clusters with different behaviors. And I will show you the 3 most interesting or prominent behaviors. So we have 10% of the students who spend a lot of time in this explore mode. And they are very systematic when they test things. So here you see that they systematically test the relations between the different weights. So these are the best performing students, not only in our post-test, but these students also tend to have the highest science grades in school and the best performance in standardized math assessments. Then there's another group of students who try really hard to test hypotheses, but they don't really know how to do it. This is just a particularly bad example where a lot of weights are put on each side and it's really hard to gain any information from it. And then, of course, there are these students who do what we call trial and error. They don't bother testing anything, but they always go to this challenge mode and answer questions until they pass the game. So we have used this cluster analysis as an assessment for how students do inquiry. But what I want to show you today, what we can also do is that we can use such a cluster analysis that we can interpret as a basis for adaptation. So let us assume that we are given a cluster solution and we have different groups and we can interpret them so we understand their behavior. What we could then do is, for each group, we could design an intervention that is supposed to exactly help this group. So if someone has trouble exploring, we could give them hints on how to set up tests, like keeping it simple and changing only one thing at a time, just as an example. Or for these students, we could hint them or force them to spend time testing so that they could also learn this part. So we could do these interventions for all of the different groups, and when we have that, and a new student enters our system, our goal would be to, as fast as possible, find out to what group the student belongs to, and then we could deliver the intervention to that student. So in order to solve this task, so as early as possible, we want to assign a student to a cluster. We have used recurrent neural network, and we have explored a lot of different types, and I will just show you a snapshot of the results, which is here in blue a random forest classifier and in red a long short-term memory. Here is the classification accuracy, so the assignment to the cluster, and here is the area under the receiver operation curve. And so the random forest classifier, we optimized it, so we trained it to predict at a certain point in time. And these were the levels of the game, so after 3 correct questions, after 4, and after 5 in a row. The long short-term memory, we optimize it to predict after each interaction of the student, so after each test and after each question in challenge mode. So the training error was optimized over the whole sequence. And as you can see, the long short-term memory is equally or a bit better, but it has the advantage that given that it can predict the cluster after each interaction of the student, we could adapt the intervention point in time for each student. So this was just a very short overview over knowledge modeling and over strategies. And when you look at the human teacher here, we see that there is still a lot of work that needs to be done in this area. Thanks a lot for your attention, and I'm glad to take questions.